What if Tesla just unveiled an engine that could completely change the electric vehicle industry? For years, automakers have battled over range, charging speed, efficiency, and battery costs. But this new technology could attack the problem from an entirely different angle. And if Tesla can actually deliver what's being promised, the biggest question isn't who will win the EV war. It's whether the war could be over before everyone else even catches up. Here's what Tesla just revealed, and why the industry is paying attention. Picture this. A dimly lit stage, a single piece of metal spinning in a technician's palm, and a room full of engineers who came expecting a car announcement and left talking about something else entirely, a motor. Not a new paint color, not a bigger screen, not another software update. A motor that several people in that room quietly admitted could reshape how every electric vehicle on the planet is built. If that sounds like an exaggeration, stay with me, because the actual engineering behind it is stranger and more interesting than the hype suggests. And by the end of this video, you will understand exactly why a spinning piece of metal has automakers from Detroit to Wolfsburg rethinking their next 5 years. For most of the last decade, the electric vehicle race has been framed as a battery story. Bigger packs, faster charging, more range per dollar. That framing was never wrong, but it was incomplete, because the motor sitting inside every EV has quietly been just as important and just as expensive as the battery pack bolted underneath it. Tesla understood this earlier than almost anyone, and the company's approach to motor design is one of the least talked about reasons it built such a large lead over legacy automakers in the first place. To understand why, you have to go back to a basic problem that every electric motor engineer has wrestled with for a century. Inside an electric motor sits a rotor, the spinning component that actually turns the wheels. The faster that rotor spins, the more torque and power you can extract from a given size of motor. But spin something fast enough, and physics starts fighting back. Centrifugal force pulls outward on every gram of material in that rotor. And at extreme speeds, that force is enough to crack magnets, warp metal, and in the worst cases, tear the rotor apart from the inside. For decades, this was simply accepted as a hard ceiling. Push a motor too hard for too long, and you either destroy it or you have to bury it in heavy reinforcement that adds weight and kills efficiency. Tesla's answer to this problem became public in a fairly unglamorous way, in engineering breakdowns of the Model S Plaid's motor, and later in patent filings and investor presentations that described wrapping the rotor in a sleeve of carbon fiber rather than the traditional steel banding most manufacturers use. Carbon fiber has a property that makes it almost perfectly suited to this job. It is extraordinarily strong for its weight, far stronger than steel per gram, which means it can hold a spinning rotor together at speeds that would tear a conventionally reinforced motor apart without adding much mass. That combination, high strength and low weight, is exactly what you want wrapped around something spinning at tens of thousands of revolutions per minute. It helps to understand where electric motor design started before we talk about where Tesla pushed it. Early production electric vehicles, including Tesla's own original Roadster and the first-generation Model S, largely relied on induction motors, a design that doesn't use permanent magnets at all and instead generates its magnetic field electromagnetically. Induction motors are rugged, relatively simple, and don't depend on rare earth materials, but they tend to be less efficient at partial loads, which matters enormously for real-world range. Over time, Tesla shifted toward permanent magnet synchronous motors for its rear drive units because they deliver more torque and better efficiency for a given size and weight, which is part of why the Model 3 and Model Y saw meaningful range improvements over the company's earliest vehicles. That shift, though, reintroduced the rare earth dependency problem, which is exactly the tension the company's newer motor work is trying to resolve: more of the efficiency benefits of permanent magnets, with less or none of the supply chain baggage. The Plaid's motor is a real, documented example of what this approach makes possible. Independent teardown analyses and Tesla's own technical materials describe the rear motor in the Plaid powertrain spinning at speeds well beyond what you would find in a typical family sedan, speeds usually associated with specialized industrial equipment rather than a car you drive your kids to school in. And the acceleration numbers that resulted are not marketing spin. Multiple independent outlets clocked the Plaid at close to a 2-second 0 to 60 time, a figure that put it in the same conversation as multi-million-dollar hypercars, all while remaining a four-door sedan that could carry a family for hundreds of miles on a single charge. That combination, extreme performance and everyday usability from the same motor, was genuinely rare when it launched, and it forced competitors to take Tesla's powertrain engineering seriously in a way they hadn't before. But the carbon fiber wrapped rotor was never really the end goal. It was a proof of concept, a demonstration that Tesla's engineers were willing to solve manufacturing problems other companies considered too difficult to bother with. Wrapping a rotor in carbon fiber at production scale is genuinely hard. Any flaw in the wrapping process, a misaligned fiber, an air pocket, an inconsistent resin cure, and the entire rotor can become unusable or unsafe at speed. Getting that process reliable enough to build hundreds of thousands of units a year is the kind of unglamorous manufacturing engineering that rarely makes headlines, but decides who actually wins in this industry. Which brings us to the part of this story that matters more than any single motor: cost. At Tesla's 2023 Investor Day, the company's powertrain engineering lead, Colin Campbell, stood in front of investors and analysts and announced something that got less attention than it deserved at the time: that Tesla was developing a new generation of permanent magnet motors that would eliminate rare earth materials entirely. For anyone who doesn't follow supply chains closely, that announcement is a much bigger deal than it sounds. The magnets used in most high-performance electric motors rely on rare earth elements like neodymium and dysprosium, materials that are genuinely abundant in the Earth's crust, but are overwhelmingly refined and processed in China, which handles roughly 70% of global rare earth production, according to U.S. Geological Survey estimates. That concentration creates a choke point. Any automaker building high-performance electric motors is, whether they like it or not, dependent on a supply chain they don't control and can't easily diversify. A motor that performs at a high level without rare earth magnets removes that choke point entirely. It is a genuinely difficult engineering problem, because rare earth magnets are prized precisely because they pack enormous magnetic strength into a small, lightweight package. And finding alternatives that don't sacrifice performance has stumped engineers across the industry for years. Ferrite magnets are one option, but they typically require more material to achieve similar output, adding weight and size. Other alternatives, like iron nitride-based magnets being explored by companies such as Niren Magnetics, are promising but still working toward automotive scale production. Tesla betting its next-generation drive units on solving this problem in-house is a serious statement of intent, not a marketing slogan. And it lines up with a broader pattern of the company trying to control every expensive link in its own supply chain, from battery cells to chips to now, magnets. That same carbon fiber wrapped rotor approach hasn't stayed locked inside a single low-volume performance trim either. As Tesla has refreshed its higher output Model 3 and Model Y performance variants, reporting and spy shots of pre-production units have pointed to carbon fiber components moving beyond the motor itself and into elements like spoilers and interior trim, evidence that the company is treating carbon fiber manufacturing know-how as a capability to be reused across the lineup rather than a one-off trick for a flagship sedan. That kind of cross-pollination, taking an expensive lesson learned on a low-volume Halo product and pushing it down into higher-volume, more affordable vehicles, is a pattern Tesla has repeated before. And it's part of why a motor breakthrough that debuts in a plaid or a performance trim tends to matter far beyond that one model. This is also where the manufacturability story becomes genuinely important, and it connects directly to a problem Tesla has been dealing with in public. The Cybertruck, once framed as a halo product that would redefine the pickup truck category, has had a rockier road than the company's marketing originally promised. Sales have consistently landed well below the ambitious volume targets Tesla initially floated, and the vehicle has been the subject of multiple recalls covering everything from accelerator pedal issues to trim panels detaching at speed. None of that means the Cybertruck is a failure in every sense. It remains a genuinely unusual vehicle with a dedicated fan base, but it has not delivered the runaway commercial momentum Tesla hoped for. And that reality has put more pressure on the rest of the company's product lineup to carry growth. a cheaper, more efficient, easier-to-manufacture drive unit that can be dropped into the Model 3, Model Y, and future lower-cost vehicles, is a far more reliable growth lever than betting everything on a single polarizing truck. And the scale of the cost ambition here is worth sitting with for a second. Tesla has publicly discussed targets for its next-generation drive units, motor, inverter, and gearbox combined. That would represent a significant reduction from what many competitors currently spend to achieve comparable performance. Even a modest gap in per-unit cost, multiplied across the hundreds of thousands of vehicles Tesla produces annually, adds up to a meaningful structural advantage. The kind of margin cushion that lets a company keep cutting prices while competitors are still trying to reach profitability on their electric vehicle lines in the first place. That is not a hypothetical problem for the rest of the industry. It is a documented one. Ford has publicly reported billions of dollars in losses across its Model E electric vehicle division in recent years, even while selling well-regarded products like the Mustang Mach-E and the F-150 Lightning. General Motors has faced its own well-publicized delays and software integration issues as it works to scale its Ultium platform. Rivian and Lucid, both smaller and newer, have continued burning through cash reserves as they work to bring manufacturing costs down to sustainable levels. This isn't a story about incompetence at any of these companies. It's a story about how difficult it genuinely is to build electric vehicles profitably at scale, a problem Tesla spent years grinding through with its own painful production hell during the Model 3 ramp, and one that gives it a hard-won head start now. There's also a human element to this story that's easy to skip past when you're talking about torque figures and magnet chemistry. Behind every one of these design decisions is a team of powertrain engineers who spent years failing quietly before anything worked well enough to put in front of investors or customers. Carbon fiber winding processes that produced unusable rotors. Magnet formulations that looked promising in a lab and fell apart under real-world thermal cycling. Manufacturing lines that had to be redesigned more than once before they could run reliably at automotive volumes. That unglamorous, repetitive process of failing and refining is the actual substance behind headlines about a single motor reveal. And it's worth remembering that the version of this technology the public eventually sees is usually the product of years of work that never made it into a press release. The one company that stands out as a genuine counterweight to Tesla globally is BYD, which has built a formidable position, especially in more affordable market segments, through vertical integration of its own battery and vehicle production. But BYD's strength has largely come from cost leadership in accessible vehicles, while Tesla has been pursuing something slightly different, trying to hold on to a performance and technology edge while also driving costs down. A harder needle to thread, but one that, if it works, is difficult for either budget-focused or premium-focused rivals to fully counter. It's also worth putting Tesla's factory footprint into this picture, because a cheaper motor design is only valuable if it can actually be built at volume in more than one place. Tesla currently produces vehicles at Fremont in California, Shanghai in China, Berlin in Germany, and Austin in Texas, a genuinely global manufacturing network that most EV startups, and even some established automakers, simply don't have the capital or the years of operational experience to replicate. Every one of those plants represents a place where a new drive unit design has to be validated, tooled, and scaled without disrupting existing production, which is a logistics challenge as much as an engineering one. The company has also discussed expanding into additional markets, including potential future production in Mexico, which would put it even closer to North American supply chains and demand. None of that guarantees smooth execution. Tesla has stumbled through painful production ramps before, most notably during the Model 3's early years, when the company nearly ran out of cash trying to get manufacturing lines working reliably. But that hard-earned experience is now a genuine asset, because the company has already lived through the mistakes that trip up newer manufacturers. It would also be a mistake to think about Tesla's motor purely as an isolated hardware win, because it plugs into a much larger and more defensible system the company has spent over a decade building. Every Tesla on the road generates driving data that feeds back into the company's autonomous driving development, and a cheaper, more efficient motor means more vehicles can be built and sold, which means more of that data flowing in. Tesla's supercharger network, once dismissed by critics as a mere convenience feature, has become such a competitive advantage in reliability and coverage that Ford, General Motors, Rivian, and other manufacturers have adopted Tesla's NACS charging connector, just so their own customers can access it. A remarkable concession from companies that spent years positioning themselves as Tesla's direct rivals. The company has also pushed to control more of its own battery cell production through its 4680 cell program, and it has invested heavily in custom compute infrastructure, including its Dojo supercomputer project, aimed at training the neural networks behind its self-driving software using real-world driving footage collected from its fleet. None of these pieces are secret or speculative. They are documented parts of Tesla's public strategy. And the new generation of drive units slots directly into that same flywheel. Because a cheaper motor means more affordable cars mean more vehicles sold. And more vehicles sold means more data, more supercharger usage, and more manufacturing experience feeding back into the next iteration of hardware. None of this guarantees Tesla wins the broader electric vehicle race outright, and it would be dishonest to suggest otherwise. Manufacturing rare earth-free motors at scale without sacrificing performance is a genuinely unsolved problem industry-wide, and Tesla still has to prove it can hit its own cost targets in real factories, not just investor day slides. Competitors are not standing still either. BYD continues to expand aggressively into international markets. Chinese battery and motor suppliers are investing heavily in their own rare earth alternatives. And legacy automakers, despite their well-documented struggles, still have manufacturing scale, dealer networks, and brand loyalty that Tesla has never fully replicated in every market. A better motor is a genuine advantage, but it is one piece of a much larger and still unresolved competition, not a single move that ends the game in one stroke. Still, it's worth stepping back and appreciating what this motor represents on its own terms. It is proof that a problem widely accepted as a fundamental limitation, the trade-off between performance and efficiency in electric propulsion, was never actually as fixed as the industry assumed. Tesla's engineers looked at a physics problem everyone else had shrugged at for years and treated it as something to be solved rather than accepted. Whether or not that translates into permanent dominance, it has already forced every serious competitor in this space to rethink what a competitive electric drivetrain actually costs to build. And that alone is going to shape the next generation of electric vehicles, regardless of which badge ends up on the hood. So here's the real question worth sitting with. Is a better motor and a rare earth-free supply chain enough to keep Tesla ahead of a field that includes BYD's manufacturing scale, the legacy giant's distribution networks, and a wave of well-funded newcomers, all racing toward the same goal? Or is this just one advantage among many in a race that is nowhere close to finished? I'd genuinely like to know what you think, so drop your take in the comments, whether you think this seals Tesla's lead or whether you think the rest of the industry is closer to catching up than the headlines suggest. If you found this breakdown useful, consider subscribing for more deep dives into the technology quietly shaping the next decade of transportation. Because this motor story is far from the last piece of this puzzle.